The layout of the periodic table. The periodic table is arranged in order of increasing atomic number. That is, as you read the periodic table from left to right and top to bottom, you'll see that the atomic number will increase consistently. We'll pull up a periodic table here, and you'll notice that here hydrogen has the atomic number of 1, helium has the atomic number of 2. That's left to right. And then top to bottom, you'll see it always increases as well. Lithium 3, beryllium 4, boron 5, 6, 7, 8, 9, 10, 11, so on and so forth. We'll be able to see a consistent trend that is never broken. Atomic number always increases as you go from left to right and top to bottom on the periodic table. Now, how is that periodic table laid out? First, it is laid out in columns. Those columns have a specific name. Those are called groups. The groups are numbered from left to right on the periodic table, and furthermore, they're broken up into two major groups, Group A elements and Group B elements. Group A elements are consisting of the S and the P blocks, which you have learned about, and the Group B elements are those D and F blocks towards the bottom of the periodic table. When we look at a periodic table that we've previously created with electron configurations, we can see that here we have everything with a electron configuration ending that contains an S. This is the S block and is a Group A element. This block over here is the P block. They all have configuration endings with a P in them, and these are also Group A elements. Whereas in the middle section we have the D block. These are Group B elements, and the F block are classified as Group B elements as well. The rows are numbered as well. They're numbered from top to bottom, 1 through 7. There's a little bit of a trick. When we take a look at the periodic table, we have a group of elements down here. These are known as the inner transition elements, or the lanthanide and actinide series. These come out of the transition elements. They're known as the inner transition elements because they could technically exist right here inside the transition elements. They would correlate with periods number 6 and 7 respectively. We can see that here on the right hand side of our screen, we've got period number 1, 2, 3, 4, 5, 6, and 7. These periods correlate with the energy level of your electrons when we're writing electron configurations. Now, Group A elements. Group A elements are essential in chemistry. In our chemistry class, we'll look very heavily at Group A elements. One of the things that's special and unique about these Group A elements is they have group numbers, and those group numbers will correlate with what's called valence electrons. Now, a valence electron in itself is the same as any other electron, but the location of a valence electron is different. Valence electrons exist on the outside of the atom. When you can think about the atom, you have a small dense center. That's the nucleus, where you have protons and neutrons. And then from there, outside of that, you'll build up more and more and more electrons. The electrons on the outside will be more likely to interact with another atom. If you thought about, my hand as one atom and this hand as a different atom, if they came close to each other, the nuclei aren't going to interact because you have electrons outside of that. But if you had 50 electrons or something of that nature, which ones would be most likely to interact with one another? The ones furthest away from the nucleus. And that's what actually happens. Just so happens that those electrons, the furthest ones out, are classified or called valence electrons. One atom, or any atom, can have at most 8 valence electrons. They cannot and they do not contain more than 8 valence electrons. Our noble gases, when we see our periodic table, our noble gases are here on the far right of the periodic table. Noble gases have 8 valence electrons. They don't react because they have stable electron configurations. That is, they have 8 valence electrons. Everything else on the periodic table has less than 8 valence electrons, and they react, they form bonds, so that they can attain a noble gas electron configuration, so that they can attain 8 valence electrons. When we think about the periodic table a little bit and take a look at it a little bit closer, how many valence electrons do different elements have? Well, elements in group 1A have 1 valence electron. Elements in group 2A have 2 valence electrons. Elements in group 3A have 3 valence electrons. Group 4A, 4 valence electrons. 5A, 5. 6A, 6 valence electrons. 7A, 7 valence electrons. And group 8A, 8 valence electrons. So the group number tells you how many valence electrons you've got. A couple of examples real quick. Boron. Boron has 3 valence electrons, and it is located in group 3A. If we look at a periodic table real quick, boron, group 3A, 3 valence electrons. Next, barium. Barium, I'm telling you, is in group 2A. It's down here, element number 56 on the periodic table. Group 2A, element 56. How many valence electrons do you think it should have? Sulfur and xenon, you should locate on your periodic table, figure out which group number it's in. Its group number corresponds with the number of valence electrons it contains. Next couple of questions. Which of the following elements has the fewest number of valence electrons? Magnesium, gallium, tin, or francium? To answer these questions, consult the periodic table. Again, locate what column or what group number each is in, and then go from there. In question 1, which has the fewest? You want the element furthest to the left. Question number 2, which of the following groups of elements consists of only elements with 7 valence electrons? Well, group 1A has 1 valence electron, group 3A has 3 valence electrons, group 5A has 5 valence electrons, so group 7A would have how many valence electrons? Does every element in that section have 7 valence electrons? This one, or this one? Make your choice. The next question, which of the following does not organize the elements listed in order of increasing number of valence electrons? So we're looking for the one that does not order them correctly. Again, our periodic table is going to be essential, where column number representing numbers of valence electrons. Group A elements. Now, these group A elements and their valence electrons, I am telling you they're important. But why are they important? The reason why they are important is because these elements are trying to be like a noble gas. In order to do that, they'll need to gain electrons or they'll need to lose electrons so that they have the same number of valence electrons as those noble gases, the ones with stable electron configurations. Now, in group 1A, what group 1A elements do, they form a positive 1 charge. The reason why they form a positive 1 charge is because they will lose 1 electron, getting a positive 1 charge. Think about lithium, for example. Lithium is element number 3 on the periodic table. That means it has 3 protons. In a neutral element of lithium, it would have 3 electrons. Well, if lithium lost 1 of those electrons, it would have 2 electrons, and it would still have those 3 protons. These 2 protons and electrons, their charges would cancel out because you have 2 positives and 2 negatives. So if those cancel out, what are you left with? You're left with 1 proton with a positive charge. So group 1A will form a +1 charge because they lose 1 electron. Group 2A. will form a positive 2 charge. The reason why group 2A forms a positive 2 charge, you can think about beryllium with 4 electrons. You lose 2 electrons, they go away, you're left with 2 bonus protons. These 2 electrons and protons cancel out. What you're left with? 2 extra protons with a positive charge, plus 2. For the same reason, group 3A could form positive 3 charges. Group 4A is a little bit different. We'll specify what's going on there with plus or minus 4. Some funny stuff's going on. Group 5A, they form a negative 3 charge. How do you get that negative 3 charge? Well, let's take a look. Periodic table, and let's take a look at nitrogen. Nitrogen is right here on the periodic table. Element number 7. I told you before that these elements, they want to be like a noble gas. They want to have the same number of electrons as a noble gas. Nitrogen is in group 5A. Neon is in group 8A. 5 plus 3 equals 8. Nitrogen wants to gain 3 electrons. If you gain 3 electrons, what charge are electrons? Negative. So you gain 3 extra electrons, you become negative 3 charge. Group 6A will form a negative 2 charge. Group 7A will form a negative 1 charge. They're going to gain 1 electron. And group 8A, they don't form charges. They don't bond. They don't react. They don't need to. They have stable electron configurations already. So their charge always remains 0. So what you can do now is you can label the groups on your periodic table with the appropriate charges. What I mean is group 1A ought to have a plus 1 charge. Group 2A should have a plus 2 charge. Group 3A, plus 3, plus or minus 4, minus 3, minus 2, minus 1, and of course 0. So make sure you label that on your periodic table. Next, group A elements and these valence electrons. We can represent valence electrons as dots around the element symbol. When we do this, when we represent valence electrons as dots around the element symbol, that's called an electron dot structure. You may have seen them before. These dots are not haphazardly placed around the symbol. We have a specific sequence in which we need to place them. That sequence is here. With element X, this is just any random element. It's a fictitious element, not real. The way we arrange our dots is we put the first dot above the element symbol, the second dot to the right of the element symbol, the third dot to the bottom, the fourth dot to the left. What that does is it puts 1 electron or 1 dot on each side of the symbol first. And then you can go back and plug in the second one. You can see after 4 comes 5, 6, 7, and 8, where we add in that second dot. So let's take a look at and try to do an example. Here we'll take a look at oxygen with 6 valence electrons. On the periodic table, it is in group 6A, so it has 6 valence electrons. When I draw in the electron dot structure, when I construct the electron dot structure, I would put my first electron here. Okay, that's electron number 1. Electron number 2 should go here. Electron number 3 there. Electron number 4 here. And then finally 5 and 6 there. That's the appropriate way to draw an electron dot structure. The reason why you need to follow that order is because the number of paired dots and single dots is essential once we get to the next level. Thank you very much for listening. I hope this is helpful. Please complete the worksheet if you need to, the PowerPoint questions. If you need to go back and pause, so be it. Make sure you save it to your desktop and you drag and drop this file into your week 11 folder. Thank you and have a great day.